proportions. So we let xi x1 up to xn. So again, there is a problem here that's supposed to be xn. So I'll check that. So let x1, x2 up to xn be the population elements of size n. Okay. So out of this, suppose n has the characteristics of interest. Okay. So the proportion of the population that has the desired characteristics will be defined by this notation pi, which is n out of n. So this is the sample size divided by the population size. So we define that by pi. Okay. So in addition, suppose the sample proportion is given by p. Okay. Then consequently, the sampling distribution involves two mutually exclusive events. Okay. So you know what we mean by mutually exclusive events. If A and B are mutually exclusive, the occurrence of one totally excludes the occurrence of the other one. So Roman 1, proportion that exhibits or have the characteristic of interest is defined as pi. Then the proportion that does not contain the characteristic of interest is given by 1 minus pi. Okay. So therefore, the distribution of p, which is the sample proportion, is binomial. So we have the distribution of p having binomial distribution with parameters n, which is the sample size, and pi, which is the proportion of the population with desired characteristics, as given here. Okay. So if you can allow me, then I can edit those errors there, just a minute. Okay. Let me correct. Yeah, so this guy, so that's supposed to be so the curly brackets there. Then we remove this. Okay, then this is 2. I think that's okay. So sorry for the typing errors. Okay. Yeah, so that is what we have. So this is Roman 2, that is xn. So then the sampling proportion has got binomial distribution with parameters n and pi. Okay. Yeah, so let's look at this theorem. So if n times pi, okay, where this is the proportion of the population with desired characteristics. So if this is greater than or equals to 5, or n into 1 minus the proportion of the population without the characteristic of interest greater than or equals to 5, then we say the distribution of the sample proportion P is approximately normal with parameters pi, which is the proportion of the population with characteristics of interest, and pi into 1 minus pi divided by n. Okay. So meaning that we say P, that's the sampling proportion, is normally distributed with mean, pi, and variance given by this value here. Okay. So that's normally if n is large, and more especially as per the theorem that's given here. So the 1 minus alpha level of confidence is therefore given by CI, which is the confidence interval estimate, is given by the sample proportion plus or minus the margin of error. So this is the margin of error in the estimation of the population proportion with characteristics of interest. So when we talk of proportions, basically we are talking about it's a fraction, it's a probability. Okay, for instance, the proportion of the student population in Strathmore who are doing PCOMs. So it's a fraction or a proportion of the entire population. So if you want to estimate that, then you can use interval estimation. Okay, so that's what we mean by the proportion. But we're talking about the component of the population which has got the desired characteristics or characteristics of interest. So if you want to know the proportion of the population, okay, who are doing maybe actuarial science, then what is the denominator? The denominator will be all the students in that campus, for example. Then the numerator will be the number of the people that you are interested in. So that fraction will give us the sample proportion, okay? The proportion of the population with the characteristics that you are interested in. Okay, so let's take a look at this example number 1. So in a given line of production, it's been found that 5 in every 100 items are defective. A random sample of size 120 was picked for investigation. The proportion of defective items was found to be 6%. Construct the 95% confidence interval for the population proportion of defectives. B, we construct the 99% confidence interval for the population proportion of defective items. Okay, so from this question, we can write down what is given. Okay, so we are given here that 5 in every 100 items are defective. So pi is given by 5 out of 100, which is 0.05. Okay, so that goes without saying that 1 minus pi, okay, is given by 1 minus 0.05, which is 0.95. Okay, then n is given as 120. Okay, then the sample proportion is a proportion of defective items. The proportion of defective items was found to be 6%. Okay, that is 6%, which is 0.06. So we want to find the 95% confidence interval for the proportion of defective items. So that's 1 minus alpha. So if 1 minus alpha, so this is now the first one. If 1 minus alpha is 95%, okay, that is 0.95. Then it means alpha is 0.05. Okay, that's correct. Yes. Can you hear me?
Yes.
Yeah, so then we can construct the 95% confidence interval. So we said the confidence interval for population proportion is given by the sample proportion plus or minus the square root of the fraction or the proportion of the population with characteristics of interest into 1 minus pi, like this, divided by n. So we take the square root of all that. Okay, so this will be okay, so times z alpha by 2. Okay, so we can go up, if we can go up here, then we have so that confidence interval is given by 0.06 plus or minus the square root of 0.05, okay? So times 0.95, that is 1 minus 0.1 minus 0.05, okay? So divided by 120, okay? So this one here, like this, times Z alpha by 2. So alpha is 0.05. So times alpha by 2 here will be 0.05 divided by 2, which is 0.0225. Is that correct? Yes?
Yes.
Yeah, so times Z alpha by 2. So our Z alpha by 2 will be Z at 0.05, 0.025, sorry. Okay, 0.0225. So from the standard normal tables that I gave you, can you get the value of Z for which the probability is 0.025? Yes. What is the value of Z here or here? Because here it means this is 0.95, the unshaded region. So what value of Z corresponds to a probability of 0.025?
1.96.
Yes, correct. 1.96 or negative 1.96. So it's 1.96. So what we have here now will be, so this is equals to, this is equals to 0.06 plus or minus, okay? So 0.05 times 0.95 divided by 120. Take the square root of this like this, then you multiply by 1.96. What do you get?
0.039.
Okay, 0.039. So you have that's 0.06 plus or minus 0.039. So that interval will be, the lower limit or the lower bound will be 0.06 minus 0.039. Is it 0.021?
Oh, yes.
Yeah, then 0. Is it 99? The upper limit. 0.099, like that. Is that correct?
Yes.
Yeah, so that is what we call the 95% confidence interval for the proportion of defective items produced. So can you do the 99% confidence interval? Please do, then let us know what you are getting in 2 minutes. Okay, so somebody is asking me to explain how we got 1.96. So we obtained that from the tables. So minor Esther.
Yes.
Yeah, so have you seen how to get the 1.96, or you want me to explain?
I want you to explain that.
Okay, so I will explain by sharing my standard normal tables. Let me see if I can access the standard normal tables. So let me open my tables, Esther, just in a few. Okay. So what did we say? We said we are looking for, Esther, I hope you can hear me. So
Yes.
we are looking for the value of Z for which the probability is 0.025. So you're seeing my standard normal table here?
Yeah.
Yeah, okay. So Esther, can you read for us this?
A table entry for Z is the area under the standard normal curve to the left of Z.
To the left, isn't it?
Yeah.
So in other words, these probabilities we have, what we have inside these tables here, inside the tables, okay, those are probabilities. That's why you don't see any negative value inside the table, okay? So these values we have, those are the areas for the shaded region here. You see the shaded region here? Yes.
Yes. Yeah.
So these values, these are the areas for the shaded region for different values of Z. So these are the values of Z. These are the second decimal. The first row gives us the second decimal point for the values of Z. Okay. So since we are looking for the value of Z corresponding to a probability of 0.025. So when we write like this, it means we are looking for the value of Z for which the probability is 0.025. So we look for 0.025 inside the table. Okay. So in my table, I can see it's here. Okay. Again, these values inside the table, they are between 0 and 1. These are 0.00, 0.00, 0.1075, for instance. Okay. Now, this is 0.0250, which is what we are looking for, isn't it?
Yes.
So what is the value of Z corresponding to that? So then you read off the value here, it's negative 1.9, and the second decimal point is here, okay? It is 0.06, okay? That is negative, isn't it? So that means this value of Z here is negative 1.96, okay? And since since the standard normal curve is symmetrical, it means that area is also equivalent to what we have here, this shaded area here in blue, okay? So this Z here must be positive 1.96 because this area is 0.025, this area is 0.025. One side of a normal curve is a complete reflection of what you have on the other side, okay? You understand? So the only difference between here and here is just that minus, isn't it? So when we are looking for the confidence intervals, okay, in interval estimation, if it's the confidence interval for the mean, then you say X bar plus or minus the margin of error. So this plus or minus will take care of this negative value here. You see this? Yeah, so I don't know whether I've explained clearly to your satisfaction.
Yes, thank you.
Yeah, welcome. But another way of doing that is also you can use the next table, this one here, okay? So again, here we are saying the values of the table entry here will give us the area under the standard normal curve to the left of Z, Okay, so these values we have here, these are the probabilities or are the areas for the shaded region here. So you can see this is slightly more than half, isn't it? Yes.
Yeah.
Yeah, so for instance, 0.975 here will be the area for the shaded region, 0.975. So what will be the remaining area here? That will be 0.02, 0.025, isn't it?
Yes.
So again, that means the value of Z here is 1.96. So you can use this table or you can use the previous one. You will still get the same value. Okay, so that is that. So you're doing some questions. So I don't know whether you've completed here. So the only difference between these two questions here is in terms of the level of confidence, isn't it? So the first one here for A, alpha is 0.05. So alpha by 2 is 0.025. Okay. For the second question, alpha is 0.01 because 1 minus alpha is 0.99. Okay. So meaning alpha by 2 is 0.005. Okay. So when we talk of the confidence interval for the population proportion given by the sample proportion plus or minus the square root of pi into 1 minus pi divided by n, okay, times z alpha by 2. So for the second question here, our z alpha by 2 is z at 0.01 divided by 2. That is z at 0.0005. So what do you get? What's the value of z for which the probability is 0.005? Do you get 2.58? Yes.
Yes.
Yeah, so this is z, which is equals to 2.58. Okay, so on this side you have z here is negative 2.58. So inside here we have 0.99. That's 1 minus alpha. Okay, so this area here is alpha by 2, which is 0.005. This area here is alpha by 2, which is 0.005. So when you say 0.005 plus 0.005 plus 0.99, that's like saying 1 minus alpha plus alpha by 2 plus alpha by 2. Do you get 1? You should get 1, isn't it? That's what we saw in our previous derivations. So the only difference between these two is in terms of this value of z. So what do you get for B? Yes. So the confidence interval is given by 0.06 plus or minus 0.05 times 0.95 by 120. Okay. Take the square root of this, then you multiply by 2.58. Okay. What do you get, class? That confidence interval is?
$0.051.
The margin of error?
Yeah, that's the margin of error.
0.051, like that?
Yeah, yes.
Okay, thank you. So what is the lower limit? 0.006 minus this?
0.009.
Yes, 0.009. Then here you have 0. Approximately 11, isn't it? 111, like that, is it?
Yeah.
Yeah, approximately to 3 decimal points. So that's how to do that. Thank you. So yeah, that's 0.009, 0.11. That's okay. So let's look at the minimum sample size to estimate the population proportion. So what is the minimum sample size required to estimate the population proportion? So if you let E be the amount of the error, okay, then of course, this is the estimate of the population proportion with characteristic of interest. So then Q is given by 1 minus the population with characteristic of interest. So this is the estimate of the population without the characteristics of interest. N is the sample size. Then this is the value of Z corresponding to the level of significance given. That's alpha. So we simply want to make, you want to make N the subject of the formula, okay? So what do? So first of all, you can divide both sides by Z alpha by 2, so that we remain with the square root of PQ by N. So how do you remove this square root on the right-hand side? We square both sides, isn't it? So when you square both sides, then you have the error divided by the value of Z squared is equals to the square of this square root here, like this square. So when you square the square root sign, then the square root sign will disappear, because that's like saying PQ by N raised to a half. So raised to 2, that's square. So this and this cancels. So we remain with the error squared divided by Z alpha by 2 squared, okay? That's equals to PQ like this divided by N. So you can make N to be the subject of the formula, okay? How will you do that? So you can cross multiply, so you have N times the amount of the error squared is equals to PQ, okay, times Z alpha by 2 squared when you cross multiply. So that you have N is given by PQ like this times Z squared alpha by 2 divided by E squared, okay? So in other words, you can say N is given by PQ, okay, times Z alpha by 2 divided by the amount of the error squared. So this is what we call the minimum sample size required to estimate a certain population proportion, okay? So given the values of P and Q and the level of confidence, okay, or level of significance alpha, and the amount of the error, then you can easily estimate the minimum sample size, okay? Or you can get the amount of the error for a given value of the sample size, the proportions PQ, and the level of significance, okay? So I hope that is clear. So E is the amount of the error. So a question here. Alan, can you read for us this question? Antonia, can you read for us this example?
Can you hear me?
Yes, I can hear you.
Okay, so a medical researcher wishes to determine the percentage of drivers using the GPS systems in their cars. He wishes to be 99% confident that the estimate is within 2 percentage points of the true population. A recent study of 180 drivers showed that 25% of them use the GPS systems. So A, how large should the sample size be? And B, if no estimate of the sample proportion is available, how large should the sample be? Yeah.
Thank you so much, Antonia. That is very clear. So the level of confidence here is 99%. So meaning alpha is 1%, that's 0.001. Okay, then we are given here we are given here the amount of the error, that the estimate is within 2 percentage points of the true population. So what does that mean? Yes, 2 percentage points. So that is 0.0, that's 0.02. Yes. Then we are given that a recent study of 108 drivers showed that 25% used GPS systems. So what is this class? What is this 25%? Can you hear me? I don't know what's happening. You're not responding. So 25% is the population with the characteristic of interest. Okay, that's the sample with the characteristics of interest. That's 25%. So Q is given by 1 minus the proportion with the characteristic of interest. So 75% do not have the characteristics of interest. That's GPS systems in this case. 0.002, that's 2 percentage points, simply means the amount of the error. So you can use this formula here to get the required population or sample size. Okay. So Z alpha by 2, we talk of 99% confidence. So this is 1 minus alpha. So alpha is 1%, okay, which is 0.01. Alpha by 2 is 0.005. So what is Z alpha by 2? It's 2.58 from the standard normal tables. You know, to get this, then you can easily estimate how large the sample size should be. Okay, and number 2, we're told if there is no prior estimate, okay, if there is no prior estimate of the sample proportion, how large should the sample size be? Then you use the proportions of P and Q to be 0.5, 0.5. That's now estimation because we are not given the prior values of P and Q. So given the values of P and Q, then you can easily also estimate that. So you simply use the formula, insert the values that are given, okay? In a given scenario, check what is given and what is not given, okay? I don't know, do you have any question? Any question? Any question, class?
Excuse me, sir. Could you kindly go over part B?
Yes?
Could you kindly go over part B?
This one?
Yes.
Okay, okay. Thank you. Then let me find out, Antonia, you have a question also? Before I respond to my friend? Or is it the same question? Okay, I'm sorry, Antonio, you're breaking. I'm not getting you. So let me respond to the other question in the meantime. So we are told if there is no estimate, okay, if no estimate of the sample proportion is available, how large should the sample size be? So we are saying in such a scenario where you are not given the prior estimates to be 25% or 30% or any other value, then we just assume that the proportion with the characteristic of interest is 50%, is 0.5. Then the proportion of the population without the characteristic of interest is also 0.5. See, now that's just estimation now. So given the size of the error and the other values or parameters in this formula, then you can estimate sample, the sample size required. Okay. If no estimate of the proportion is given. You see in our question here in A, we are given that the estimate of the population with the characteristic of interest is 25%. So in that case, it's given. When we are not told what P should be or Q should be, then we use this. Is that clear?
Yes, yes, it is. Thank you.
Okay. So Antonia, can you come up again?
Excuse me, sir. Can you hear me now?
Yes, I can hear you.
Okay. Yeah, I had the same question with that was
Yeah.
asked, but you've
Yeah.
you've explained it.
Hello, Antonia.
Yes, sir. Can you hear me?
Oh, yes, I can hear you. So you're saying I have explained your question?
Yes.
Okay, okay, thank you. So I think that is okay. So can we can take a short break of 10 minutes, then we come back. Okay. Let's break for 10 minutes, then we come back at 11:13. Thank you. So can we continue now? Yes. Can we continue now, class? Can you hear me?
Yes.
Okay. Thank you. So this is just to mention the confidence interval for population with unknown variance. So when the variance is not known, then normally if the population variance is not known, then we use the sum of variance. So Sx here, or Sx squared, is the sum of variance, or Sx is the standard deviation, the sum of standard deviation. So if that variance is not given, then we use this approximation here. So we are not using the standard normal tempo here, okay? The standard normal tempo. So we are using the T distribution tempo. So you can see this is what we call the T distribution tempo, or the T value at n-1 degrees of freedom. So n-1 here is what we call the degrees of freedom. So if we are to find the confidence interval for mu, then we say mu is given by x bar plus or minus the margin of error. So when sigma squared is not known. So in this case, where the margin of error is given by x, that's the standard deviation, the sample standard deviation of x divided by the square root of n, where n is the sample size, times the value, the student's T distribution value at n-1 degrees of freedom, okay, at alpha level of significance, or at 1 minus alpha, 1 minus alpha confidence interval. Okay, so this is the margin of error that we are going to add here to estimate the finite population mean mu at that interval of 1 minus alpha confidence level. Okay, so in this case, sigma squared is not given. So instead, we are using the sample standard deviation. So the sample must be given if sigma squared is not known. So you calculate the sample variance, then you divide by the square root of n. So you know to get the sum of variance, okay? The square root of 1 over n, the sum of yi or xi minus x bar squared, okay? So from your standard normal tables, I believe there is a page which has got what we call the students, it's called the students T distribution table, okay? Let me share my table here. I believe it has got the students T. Yes, there is. Okay. So let me share this table here. So you can see my table. Yes.
Yes.
Yeah. So this is what we call the students T distribution. Students T distribution table. Okay. So it's called students T distribution. Students because the person who developed this table was a student at that time. Okay. So we have what we call the critical values, or the probabilities. So the first column here is what we call DF. Okay. So this is DF, meaning DF means decrease of freedom. So if the sample size, for instance, if n is equal to 23, then decrease of freedom are given as n minus 1, so 23 minus 1, so 20, that will be 22. if if n is equals to 15, then the degrees of freedom df will be n minus 1, which is 15 minus 1, which is 14. Okay, so if the level of if the confidence level is 99%, so that means alpha will be 1%. So 1% is 0.01. So we are talking about t at n minus 1 alpha by 2. For example, if it's alpha by 2, just using this as an example. So if alpha is 0.01, so alpha by 2 will be 0.005. So you divide this by 2. So we are talking about the student's t distribution value at 14 degrees of freedom, okay, and 0.005. So this is the, I'm just showing you how to reach the table value for students t. So degrees of freedom is 14 because n was 15, then n minus 1 is 14. Then at 5%, 0.005 level of significance. So that value is going to be here. You see, that's going to be 2. This value is going to be 2.977. Are you seeing that, class? Yes. I'm just showing you how to read the student's t distribution table. So is that clear?
Yes.
Yeah, so so that's just how to read it. If the situation requires you to use the student's t distribution table, then the first column is the degrees of freedom. Then the first row here will give us the different values of probabilities. That's the levels of significance. Okay, so we shall not dwell much into that. What we shall do now is to look at something else, what we call the hypothesis testing. So we shall come across a number of examples when we are dealing with hypothesis testing that involves the use of students' t distribution. So we shall be using those tables again most of the time. So in which case, I believe we shall be able to understand more. So these are exercises for you. Your own time, I've given you the solutions to each exercise. So take your time, go through the questions, solve, then compare your answers with what we have here. So I've given you the solutions to each question. So now, allow me to just briefly introduce what we mean by hypothesis testing. Okay. Maybe for around 20 minutes or so, then we call it a day. Yes, so this is what we call test of hypothesis, or you can call it hypothesis testing. Okay. So first of all, what is a hypothesis? Okay, so hypothesis is a verbal statement. Okay, it's a claim or an assertion, okay, about a population parameter. Okay, that's what we call hypothesis or statistical hypothesis. You claim that this parameter is like this and that. So it's a claim. It's an assertion or a tentative statement concerning a population parameter. So for instance, if a manufacturer will claim that maybe the fluorescent tubes, okay, or some electrical appliance will last for 1,000 hours, okay, or 3 years or 5 years. See, that's a claim, okay? That's just a statement. So if you want to know the validity or how that value, I mean, if that value or if the statement are mentioned or given by the manufacturer or the seller, if you want to know whether it's true or otherwise, then you are supposed to carry out what we call hypothesis testing. Otherwise, as it is just a claim which has not been proven to be true or false. Okay, so that assertion or a claim that this electrical appliance will last for 5 years is hypothesis. Okay, that's an hypothetical statement. So you're saying a hypothesis test is a process that uses sample statistics to test a claim about the value of a population parameter. So if a manufacturer claims that a battery lasts for an average of 1,000 hours, then for you to confirm whether this is true or otherwise, then you take a sample, okay? Then you can carry out the test of that claim, okay? So given some historical data in terms of the performance of these batteries here, then on average, you can check how long such a material or such an item can last. On the basis of that, you can either reject the hypothesis or the claim given by the seller, or you can accept. So in hypothesis testing, we look at the statements, look at the tests, look at the proofs, then we make a final decision whether to accept the claim or reject the claim. Okay. So, and normally that's the basis for the issuance of what we call warranties. Okay. You buy an equipment, then you are told it has got 3-year warranty or 4-year warranty. Okay. So that's because some tests have been carried out that this material will be very efficient. It will work effectively for a minimum period of 3 years or 4 years. Okay. So because hypothesis testing must have been carried out. So we normally state the hypothesis in twos. There is one which is called the null hypothesis. The other one is called the alternative hypothesis. So one represents the claim. The other one is the complement of the claim. Okay. So if the seller or the manufacturer is telling you on average, that's mu, okay, this material will last for 1,000 hours, okay. Then for you as the consumer, then you just don't go by what the seller is saying. So then you say, what if it's not equals to 1,000 hours? Then what happens? So this is the claim. That's the claim by the seller or the manufacturer. Okay. Then this is the complement you are giving. Okay. And more specifically, what if the average life is less than 1,000? Okay. Then what happens? Will you be given warranty or otherwise? Will you be compensated for the loss or something like that? Okay. So one of the claims or one of the hypothesis represents the claim. The other one is the complement of that claim. Okay. And when one of these hypotheses is false, then the other one must be true. Okay. So if this is true, okay, based on the sample data that is given, okay, then this one is false. Okay. And if this is true, then it means the claim by the manufacturer is false, like that. So we shall see the procedures of carrying out the hypothesis testing from the formative stage to the conclusion stage. So types of hypothesis, so we are saying we have two. The null hypothesis, that is denoted by H naught. Okay. Whenever you come across this notation, you know that that is null hypothesis. Okay. It contains the statement of equality. So that's how we are going to know what is the null hypothesis. Because normally when you're given a question, nobody will tell you this is the null hypothesis, this is the alternative hypothesis. Okay. It's upon you to carry out the interpretation of the statements and know what is the null and what is the alternative hypothesis denoted by HA. Okay, so alternative hypothesis HA, this is the complement of the null hypothesis. So this is a statement or a claim that must be true if the null hypothesis is false. So this one contains the statements of inequality. So this one has got the less than, not equals to, or the greater than inequalities, okay? But null hypothesis contains statements of equality. So greater than or equals to, less than or equals to, or equals to, okay? Then that is how to represent the null and the alternative hypothesis, okay? So to write H naught or HA, null or alternative, we translate the claim made about the population parameter from a affable statement to a mathematical, statement okay? So it's very easy to see. So take a look at this example. A manufacturer claims that its rechargeable batteries have an average life of at least 1,000 charges. So I've underlined this intentionally because this is where we have the hypothesis, okay, the claims of an average life. So average, that's mean, mu or expected value, and what have you, okay? So it has got an average life of at least 1,000. So at least means greater than or equals to, isn't it? Yes. Yeah. So yeah. So that means definitely this is how the null hypothesis will look like, because we said null hypothesis contains the equality assigns equals to, less than, or equals to. The alternative hypothesis has got the less than, not equals to, or greater than inequalities. So this is equalities, okay? This is inequalities. That's how we derive or construct the null and the alternative hypothesis. So once you know what the null hypothesis is, then it goes without saying we have the alternative hypothesis. If the null hypothesis is greater than or equals to 1,000, that is the claim by the manufacturer. So you as the consumer will be saying, what if this average is less than 1,000? Okay, the complete opposite of what the manufacturer is claiming. Okay, so that will open now the basis for bargaining for the warranties and the prices and all that. Okay, that's in real life. What if it fails to last for 1,000? What will happen? Okay, so the alternative is a complement of the null. It's a complete opposite of the null hypothesis. So for instance, if we are saying H naught mu is equals to 1,000, then what will be the alternative? The alternative will be not equals to 1,000. If this is, if the null is the claim. You understand?
Yes.
Yeah. And again, not equals to, now this is what we call a two-sided. This is a two-sided hypothesis, because not equals to can mean less than or greater than, isn't it? So we call that two-sided hypothesis, and we are going to look at that later on. Okay, so there are what we call the errors that are made in the process of testing the hypothesis. So no matter which hypothesis represents the claim, we always begin the hypothesis testing, assuming that the null hypothesis, H naught, is true. So at the end of the test, one of the two decisions will be made, either to reject the null hypothesis, or we fail to reject the null hypothesis. Okay, so if H naught is that mu is greater than or equals to 1,000, then we are testing that against the alternative hypothesis that mu is less than 1,000. So this is the claim. So what we are testing is the alternative, the null hypothesis. We want to test this claim if it's true or false. Okay, so we can only make a determination whether this is true or false based on the sample data that is given. So on the basis of that, we shall now say that the null hypothesis is rejected, or we fail to reject the null hypothesis. This is based on evidence. Okay, that's why we are not talking about accept the null hypothesis, okay, or accept the alternative hypothesis. We say we reject the null hypothesis, okay, or we fail to reject the null hypothesis if it is true. Okay, so in the process of doing that, then there are two types of errors that are incurred. One is what we call the type 1 error. This one occurs if the null hypothesis is rejected when it is true. Okay, so you see you are making an error if this claim is true. Okay, but in your conclusion you're rejecting, okay, the null when it is true, then you are committing an error. That error is called type 1. Type 2 error occurs if the null hypothesis is not rejected when it is false. So you see, when the null hypothesis is false, then you should reject. Okay, but if you fail to reject and it is false, then it means you are making an error. That error is called type 2 error. Okay, so that one takes place if the null hypothesis is not rejected when it is actually false. Okay, so we can look at this table that will enable us to understand what we mean by type 1 and type 2 error. Okay, so what we have here is what we call the actual truth of the null hypothesis. Okay, so in the actual sense, the decision has been made that H naught is true, or the actual truth of the null hypothesis is that it is true. Okay, like this. So allow me to let me draw this way. Okay, let me draw this way, like this. Okay, so this is the actual situation of the null hypothesis. It is true. Okay, but which decision do you make here? You fail to reject the null hypothesis when it is true. So that is correct decision, isn't it? So you cannot reject the null. If you fail to reject the null hypothesis when it is true, then it means you've made the correct decision. Okay. But if you reject the null hypothesis when it is true, then you are making an error called type 1 error. You understand? Yes. So you do not reject the null hypothesis, okay, when it is true. Then there is no error made because that is the correct decision. Okay. In other words, you are saying you accept the null hypothesis when it is true. Then that is the correct decision. Are you getting me, class?
Yes.
Now, if the null hypothesis is false, okay, but you do not reject the null hypothesis, then you're making an error, isn't it? You're supposed to reject the null hypothesis if it is false. But if you fail to reject the null hypothesis, yet it is false, then you are committing an error called type 2 error. Okay? So type 2 error is committed by failing to reject the null hypothesis when it is false. Okay? Number 2, if you reject the null hypothesis when actually the null hypothesis is false, then you are making the correct decision. You are rejecting it when it is false. That is the correct decision, so there is no error made there. So get the difference between type 1 and type 2 error. because we shall be referring to that as we go along. So an example here, a certain college claims that 94% of their graduates find employment within 6 months of graduation. What will a type 1 or type 2 error be? Okay. So what's the claim? The claim is that 94% of their graduates find employment within 6 months. Okay. So that's it contains equality sign, 94%. We are not told at most, at least, greater than, or less than. So we take that to be the claim. So then the alternative hypothesis will be that proportion is not equal to 0.94. It can be less or it can be more. So we are simply writing the complement to H naught. So this is the complement of the null hypothesis. Okay. So the one error now will be population proportion is 0.94, but that is rejected. Okay. Meaning that if you believe that that proportion is not 94%, okay, then you are refuting the claims made by that college. Okay. So the population proportion is 0.94, but is rejected. Then you are making the type 1 error. Okay. So type 1 error is made when you reject the null hypothesis, when actually the null hypothesis is true, isn't it? So I think that's clear. Then type 2 error, the population proportion is not 0.94, but is not rejected. Okay. So type 2 error is committed when you fail to reject a null hypothesis when it is false. Okay. So I don't know whether you are getting that. So still defining terms here. So we have what we call the level of significance, that is alpha. Okay. So in the context of hypothesis testing, the level of significance is the maximum allowable probability of making a type 1 error. The maximum allowable probability of making a type 1 error. That corresponds to the level of significance. Okay. So again, most of the time that is given. So we normally carry out the hypothesis testing based on the level of significance alpha. Okay. And we have most commonly used levels of significance. So we are normally told to test the hypothesis at 10% level of significance, meaning when alpha is 0.1, or carry out the hypothesis testing for a given scenario at 5% level of significance. So that means when alpha is 0.05, okay, like that. These are the most commonly used levels of alpha. Okay. So the probability of making type 2 error is normally denoted by beta. Okay. That's normally the most commonly used notation. So once you state the null hypothesis and the alternative hypothesis and specify the level of significance, then you can take a random sample from a population so that you can calculate the sample statistics. Okay. So we have what we call the test statistic. So the statistic that is compared with the parameter in the null hypothesis is called the test statistic. So when we are carrying out hypothesis testing, there is what we call the table value. Okay. At a given level of significance alpha, then you can get the corresponding value, that's Z alpha by 2. Then there is what we call the value of the test statistic. Okay. So if it's the mean X bar, then you can compute the mean X bar, then compare this value with the table value obtained, on the basis of which you will now decide whether to reject the null hypothesis or to accept the null hypothesis. So we shall follow those procedures step by step until we know how to test the hypothesis. So this is just an example of what we mean by the test statistic. Okay, these are population parameters, mu, the population proportion. This is population proportion. Okay, then this is the population variance. This is the sample variance. Okay, this is the sample proportion. Then this is the sample mean, X bar. These are, we call them test statistics because these are values that can easily computed from a given sample. Then at different levels of significance, then you can get the standardized test statistics, the table values for different values of sample sizes. Okay. So this is how we can use the standard normal random variable Z. This is standard normal. Okay. So we use this when the population is normal or approximately normal. So this one has to be given or specified. Okay. Or when n is greater than or equals to 30, and we are not told the population is normal, then we can approximate this to normal with mean mu and variance sigma squared. We can also use this when sigma, that's the standard deviation, is null. Then you can use the standard normal tables. Okay. That's sigma by the square root of n, z alpha by 2, for example. So alpha is when n is greater than or equals to 30. So if that is not the case, then use what we call the students T distribution tables denoted by the small t. Okay. So we use this when the population is normal or approximately normal, or when the sample size is less than 30 and the standard deviation of the population is not known. Okay. Then in place of sigma, we use S, that is or S squared. In place of sigma squared, you use S squared. That's the sample. That is the sample variance. Okay. Then we have what we call p-values. So if the null hypothesis is true, then a p-value or probability value of hypothesis test is the probability of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample data. Okay, so this is the probability value that is obtained from the tables. So from the sample data, sorry. So the calculated probability or the p-value is the estimated probability of rejecting the null hypothesis of a study question when the hypothesis is true. So all these hypothesis testing are carried out assuming that the null hypothesis is true. Okay. So we shall see how to get the p-values. So a smaller p-value means that there is a stronger evidence in favor of the alternative hypothesis as opposed to the null hypothesis. So that is the basis for a rejection of the null hypothesis. Okay. Then we have 3 types of tests. Left-tailed, okay. We have the right-tailed test, two-tailed test. So we are going to see what that means by looking at the sketches of the normal curves. So the type of test depends on the region of sampling distribution that favors a rejection region of the null hypothesis. Okay, so that's given by the null hypothesis, alternative hypothesis A. So this is what we mean by the left-tailed test. So the null hypothesis contains the less than inequality sign. Okay. So this one, when we come across such a hypothesis, that means left-tailed test. You look at the alternative hypothesis, it is less than. So you can see this is what we call the p-value, okay, the area of the shaded region. So this is the area to the left of the test statistic, okay. So if you compute this value from the sample data, okay, then you can check against the p-value, okay, that's for the shaded region. So we're just illustrating what we mean by the left-tailed test. When the alternative hypothesis has got the less than sign, then we say that this left-tailed test. Okay, so it's a very interesting stuff to look at. Then next, right-tailed test. That's when the alternative hypothesis contains the greater than sign. Okay, so if you are given that the alternative hypothesis contains this kind of sign, then without being told what H naught is, then you should simply know that it's the opposite of this. So meaning it's less than or equals to a certain value K, where K is a constant. So graphically, this is what we mean by the right-tailed test. Okay, the area to the right of Z alpha. Okay, the area to the right of the test statistic. That's the right-tailed test. Then finally, two-tailed test. So where the null hypothesis contains the inequality sign, then this is what we call the two-tailed test. Check the nature of the alternative hypothesis, not equals to. Okay, so not equals to meaning it can be greater than or it can be less than. Okay, so we can combine it this way. P value is twice the area to the left of the test statistic. Here, P value is twice the area to the right of the positive test statistic. Okay, this is what we call the test statistic. This is the test statistic. So we are going to see how to compute the test statistics for different scenarios. Okay. I think that's enough introduction to hypothesis testing for now. So we can continue from there in our next class. Is that okay? I'm tired. I will share these notes with you so you can read in advance. So can we stop there, class, for today? Can we?
Yes.
Yes, sir. So I will share with you the takeaway assignment that's in place of Cat 2. I will do that Monday. Okay. Do you have any question? Any question? Antonia, do you have any question?
Not really, sir, but if I do, or if any of my colleagues do, I think I'll just share it with you.
Okay, no problem.
Okay.
Thank you and enjoy your weekend.
You too, sir.
Okay.